Today's lesson will be lesson 2.04, the in-betweeners. So today's objective is, given an exponential function, I can correctly calculate the output for a rational input in 2 out of 2 problems. Now, rational, there's a word that we haven't used yet. That's a vocabulary term we'll be talking about in just a second. But we are talking about exponential functions, so we remember this is of the form a times b to the x, or if we were to graph it, it would look something like this. So exponential functions. And one thing to think about, what does it mean when an exponent is a fraction? So we're dealing with fractions today. You know that can get people's anxiety up. We're going to go through it methodically and see if we can come up with some cool ways to explain this. So first, a few notes on fractions. A rational number, there's that vocabulary term we talked about in the objective. A rational number is a number that can be written as the quotient. When we say quotient, we mean that we're dividing the quotient of 2 integers. So basically what we're saying is a fraction. A rational number is the same thing as a fraction. And let's look at improper fractions really quick. This is likely a review, but just to make sure we know what we're looking at here. So there are 3 circles here. We're going to call these 1 whole each. So if we were to count these, they'd be 1, 2, 3. And if we were to count up by thirds, you can see these are divided into 3 each. Then we'd start with a third, which would be this bit right here. And then we add another third, and that would be 2 thirds. We add another third, and that's going to be 3 thirds. And remember, we can reduce 3 thirds. 3 divided by 3 is just 1. So 1 is another way to write 3 thirds. Now if we go up by another third, that's going to be 4 thirds. We're writing this as an improper fraction so we can see this pattern of counting by thirds. So we'll go up by another third, and this is going to be 5 thirds. We'll go up by another third, and that will be 6 thirds, again reducible to 2. So we have 2 whole circles colored at this point. And we could keep going. We could keep counting 7 thirds, 8 thirds, and the last one would be 9 thirds here, which reduces to 3. So you can see we just kept the same denominator, thirds, the whole time, everything over 3, and then we just counted up 1, 2, 3, 4, 5, 6, 7, 8, 9, and it would continue. We'd go 10, 11, 12, everything over thirds when we're counting by thirds. So that's just a reminder how we do improper fractions. So let's look at our exponential function now. The sequence below is geometric. All right, so remember this means multiplication. Also means exponential. And we need to fill in the missing terms and write the equation. Okay, so we remember our form for the equation is f of x equals a times b to the x. A is our value at 0. B is our common ratio. So our method to do this was, we realized we're going to multiply by the same thing at each step. So there are 4 steps here, 1, 2, 3, 4. And we're going to say we're going to multiply by r each time, r for common ratio. So this is 4 r to the 4th, because there are 4 of them, 1, 2, 3, 4, equals 64. We divide both sides by 4, and we get r to the 4th equals 16. Now to get rid of that r to the 4th, we need to do this fancy 4th root. We talked about how to do that in your calculator. It's probably a symbol that looks something like this, or there might be a y underneath, something like that. we can just put this in our calculator. We get 4th root of r to the 4th. Those will cancel, and then we have to 4th root this side as well. So if we 4th root 16 in our calculator, we get r equals 2. And we can see if we come up here and multiply by 2 now, we get 8, 16, 32, and indeed 64. So it all worked out. Our equation using this form is f of x equals value at 0 times common ratio to the x. So that is our equation, 4 times 2 to the x. Now, we've been using this term sequence pretty much this whole semester, but we haven't actually defined it yet. So let's actually talk about the definitions of a sequence. Is inputs are whole numbers. It's a pattern where the input is a whole number. So 0, 1, 2, 3, 4, those are whole numbers. This is a geometric sequence because we're multiplying at each step. And it's asking here as a reminder about discrete and continuous functions, is this discrete or continuous? If our inputs are whole numbers, is this discrete or continuous? Remember, this key thing we can ask is, does this value exist? Do we have a value at 1/2? Or at 1/3? Well, we said the inputs are only whole numbers, so no, these inputs are not valid. So this must be discrete, because if it were continuous, all of these values in between would have to be valid. So it can't be continuous, it's going to have to be discrete. Here's the graph of this sequence. This makes it a lot easier to see that this is discrete because the dots jump, right? We think discrete dots. So this is 4 times 2 to the x as an exponential discrete function. But now we're going to extend that. And we're going to make it a continuous function instead of discrete. We're going to connect all the dots with a curve. And we're going to ask, how would we actually find the precise value of 1/2? How would we find the precise value of 3/2? Or 5/2? We know that to go between whole numbers, we just multiply by 2, but what about these halves? Not sure. We haven't talked about how to do that, so let's take a look. So this is the same table we just filled in, right? We're multiplying by 2 for each whole step. And I've just added half steps in between each of these. So now we have 1/2 and 3/2 and 5/2, and we're just counting up by half. So 0, 1/2, 2/2, which is 1, 3/2, 4/2, and so on. And we want to find what these in-between values are. So this is Tahani and Travis. They're going to help us figure this out by working together. Thanks, friends. So Travis has an idea first. It says, if the function doubles each time x goes up by 1, so these are doubling, then half that growth happens between 0 and 1/2, and half happens between 1/2 and 1. So half and half. And so it makes sense to just find the number in between. So the number immediately in between 4 and 8 is 6, because 4 plus 2 is 6, and 6 plus 2 is 8. So halfway in between those two is 6. And to fill in the rest of this table, well, let's see, we need to find the number halfway between 8 and 16. This is similar to finding the average. We can just do 16 plus 8 divided by 2. That's going to be 24. 16 plus 8 is 24 divided by 2, which is 12. 12 is halfway between 16 and 8. We could do the same method to find the one in between 16 and 32. That's going to be 48 divided by 2 is 24. And our last one, 32 plus 64 divided by 2 is going to be 96 divided by 2, which is 48. That was just really quick, finding the average between two numbers. And it's not super important to know how to do that right now, but just realize that this is halfway in between these numbers, right? 12 is halfway in between 8 and 16. 24 is halfway in between 16 and 32, and so on. So that's a good guess for these in-between values. Let's put it in Desmos, good old handy Desmos, and see if those values line up. Well, it looks like the dots that are at whole numbers that we did before, those ones are right on the curve. But these other ones are kind of a little bit off, just very slightly off. What's going on there? Why are those dots off? What do you think? Well, let's look at our pattern. Let's look at what's happening to our numbers here. So to get from 4 to 6, we said we're adding 2, right? Because we added 2 and added 2 to make it halfway in between. And then similar here, halfway in between was 12, so we needed to add 4 and add 4. And then we added 8 and added 8. And here it looks like we added 16 and 16. But remember, this is a geometric sequence or an exponential function. For geometric sequences and exponential functions, we're multiplying at each step, not adding. If we're adding at each step, we've turned it into an arithmetic. So what actually happened here is we made little tiny arithmetic sequences. That is a little tiny arithmetic sequence, as is this one, adding 4. We made straight lines. We made a sequence of straight lines. So this program doesn't like to draw my lines right on it, but basically straight lines that are following the dots like that. Rather than being exactly on the curve, we're drawing straight lines between those dots. Let's see if I could just draw these by hand. But we'll see. I can't really draw straight lines. There you go. So straightish lines. Those are what we actually graphed. We graphed the point in between, in the middle of this straight line between those two dots, rather than the point that was actually on the curve. So Tahani says, that was a great suggestion, Travis. Even though it didn't quite match up, it really helped me see some differences between arithmetic and geometric sequences. Now, since this is a geometric sequence, maybe we need to multiply by the same number instead of adding by the same number. So let's try that method we used before for finding missing values in a geometric sequence. Let's say we're multiplying by k here, just to throw in another variable, just for funsies. We take 4, multiply by k twice, and then we get 8. So 4 times k is 8. K times k is k squared, so 4k squared equals 8. We'll divide both sides by 4 to get k by itself. We get k squared equals 2. And now to get rid of that square, we're going to square root both sides. And we get k equals square root of 2. What? That didn't evenly root? Oh, that's annoying. Why did it not evenly root? But that is actually fine. We can still use square root of 2. There's no reason we can't. So 4 times square root of 2 is just 4 root 2. And remember, root 2 is just a number. You can actually put that in your calculator. If I put that in my calculator, I get root 2 is about 1.414. So if I multiply that by 4, I get a number that's like 5.66 with more decimals that go on and on. 5.66. So about 5.66. Now what happens when we multiply by root 2 again? So we have 4 times root 2 once, what we did here, and then times root 2 again here. We're going to multiply by root 2 the second time. Well, when we multiply something by itself, that's a square, right? Root 2 times root 2 is going to be root 2 squared. So we get 4 root 2 squared. But now the root and the square cancel. So we just get 4 times 2, which is 8. And you can see, indeed, we were supposed to get 8. All right, so we multiply by root 2 again. That's our common multiplier here. We get 8 root 2. Once again, if we want to multiply by root 2 for the next step, we get 8 times root 2 times root 2. That's going to be 8 root 2 squared. The square root and the square cancel. We get 8 times 2 equals 16, which is exactly what we were looking for. So this pattern continues. We get 16 root 2, 32 root 2, and that is how we fill in these tables. So let's look at Desmos again. Let's ask Desmos, does it fit on the graph now? Look at that. It falls right on the curve. There. Totally works. We got the correct values for the in-between, and we did it by multiplying by the same number at each step. In this case, we multiplied by root 2. Now remember, this is the same as the function we did before, the geometric sequence where we were multiplying by 2 for each whole step. We just found what we needed to multiply by for in-between steps, which was root 2. So let's take a look at these values and plugging in for the function and see if we can come up with any conclusions. So f of 0, I'm going to plug in 0 for x here, and I just get 4 times 2 to the 0. And now I'm going to look at my table where my input value is 0 and see what the value is, 4. So 4 times 2 to the 0 is 4. Well, that makes sense with what we've defined for 2 to the 0, right? That means 2 to the 0 has to be 1 because 4 times it is 4. 4 times 1 is 4, so this has to be 1. Let's look at this for 1/2. 4 times 2 to the 1/2 equals 4 root 2. Okay, so 4 times 2 to the 1 is going to be 8, which again makes sense because 2 to the 1 is just 2, and 4 times 2 is, in fact, 8. And then 4 times 2 to the 3/2 is 8 root 2. So what can we conclude from this? Let's zoom in on this one in particular. What does this seem to imply about fraction exponents? Look, we have 4 times 2 to the 1/2 equals 4 times root 2. If we divide both sides by 4, those 4's are all going to go away. And we get 2 to the 1/2 equals root 2. So this seems to imply that a 1/2 exponent is the same thing as a root 2. 1/2 exponent turns into root 2, or square root of 2. Interesting. Well, let's see if that pattern continues. Let's try dividing it up by 3 this time instead of by 2. So we're going to use the same method. We have 3 steps here. Let's say we're multiplying by m. Again, we can use whatever variable we want. So since we have 3 m's this time, this is going to be m cubed. We get 4m cubed equals 8. Divide both sides by 4. We get m cubed equals 2. And now we need to cube root both sides to get rid of that cube. The cube root and the cube are going to cancel. We will get m equals cube root of 2. Okay, so that is the number we're multiplying by each time. We're going to need to multiply by cube root of 2. And once again, this is just 4 cube root of 2. Now what happens when we multiply that again? Let's see, 4 times cube root of 2 times cube root of 2. Well, that's 2 of those. That means we're going to square it, but we cube root it, so that actually doesn't cancel out at all. It just becomes the square. So the writing on it looks a little bit complicated, but we'll get through it. 4 times cube root 2 squared, just because there are 2 of them, right? Cube root 2 squared. That's exactly what it is. So it's just 4 cube root 2 squared. We're going to multiply by that cube root 2 one more time. So we've done it twice now. Multiply one more time. And I know this is getting overwhelming suddenly. All this notation is like, what is happening? But watch how this resolves. So we have 4 times cube root of 2 times cube root of 2 times cube root of 2. Because we multiplied it 3 times, right? Well, since we have it 3 times, that means it's a cube. So it's going to be 4 cube root of 2 cubed. Now the cube root and the cube cancel, and we just get 4 times 2, which is 8. It worked! So now we just repeat this pattern. We found the correct number to multiply by each time, so this is going to be 8 cube root of 2. This will be 8 cube root of 2 squared, and then 16. 16 cube root of 2. 16 cube root of 2 squared, and then the next one will be 32. Now remember, these can always, you can put these in calculator and it'll be a number. So you can do 4, let me put in my calculator, 4 times cube root of 2, and that's going to be 5.04, about 5.04. So remember, this looks fancy and complicated, but it's really just a decimal number. You can put it in your calculator and round it and just write it as a decimal. So 4 times cube root 2 squared is going to be 6.35, and so on. So all of these can be written as decimals. So let's do the same thing with these functions that we did before with the 1/2. F of 0, we're going to put 0 in for x. This is exactly the same as we did before. 4 times 2 to the 0. Our value at 0 is 4. 4 times 2 to the 1/3. Once again, we're just substituting 1/3 in for x. Well, that's going to be the value at 1/3, which is 4 cube root 2. 4 times cube root 2. Our value at 2/3 is 4 times 2 to the 2/3, which is 4 cube root 2 squared. 4 cube root 2 squared. Okay, so let's zoom in on this one again. And is this similar to what we concluded before? Well, yeah, look, so we had 3 in the denominator now, and it looks like it turned into a cube root. Remember, we can cancel both these 4's by dividing by 4, and we just get 2 to the 1/3 equals cube root of 2. So it seems like the denominator in this exponent turned into the base of the root. That was similar with the 1/2, right? We said 2 to the 1/2 was the square root of 2. So this denominator turns into the base of the root. Denominator to the base of the root. Now this one had a little bit more complication to it because we also had this, 2 to the 2/3. What's happening here? Well, it looks like we have that same cube root for the denominator, and then the numerator actually just stays. The numerator is still just an exponent. So the denominator became the base of the root, and the numerator stayed an exponent. Well, that's neat. That's a really cool pattern. So we can generalize both of these rules as a to the 1 over n is just the n root of a. So the fraction exponent and the root mean the same thing. N is the denominator and the exponent is the same thing as n root. And if we have a numerator in that exponent, well, we just keep it as an exponent. So a to the m over n is the same thing as a n rooted raised to the m. So our m exponent stayed an exponent. Our n denominator became a root. So these are a couple more exponent rules that we derived today. And that takes care of today's objective. Given an exponential function, I can correctly calculate the output for a rational input. Remember, rational means fraction, in 2 out of 2 problems. So we can use those formulas that we derived to calculate the output for fraction exponents.